If you're an aviation maintenance technician student, look, you have to master hydraulics, structures, electrical systems, propulsion, all that complex stuff.
Absolutely.
But here's the core truth. All that knowledge, it's basically useless if you don't master this foundation.
Mm-hmm.
We are talking about inspection concepts and techniques.
Mm-hmm.
This is probably the single most critical element of airworthiness.
Okay.
And, well, that means your entire career.
That's spot on. Inspection. Think of it as the ongoing audit. It's what proves an aircraft is safe to fly. It's the operational process that validates all the engineering behind it.
Right.
So our work today is really to analyze the full spectrum of inspection. We're taking the source material, the regs, the manufacturer guidelines, the sometimes complex techniques, and showing you not just what the rules are,
But the why behind them.
exactly why they exist, and crucially how you, as the future AMT, must apply them out there in the hangar.
We've got a stack of info here. We're covering the mandate for airworthiness itself, the heavy legal weight of documentation, so important, the required technical data from the FAA and manufacturers.
Yep.
And we'll wrap things up by getting into the very specific, sometimes sophisticated world of non-destructive inspection, or NDI.
NDI, yeah, that's a big one.
We're really aiming to give you the context you need, the ability to spot that subtle, maybe almost invisible defect before it turns into something catastrophic, something life-threatening.
That's the goal, preventative.
So let's start with the ultimate why, right? The whole philosophy behind continuous airworthiness, #tag1, the philosophy of airworthiness and inspection systems.
Okay, so at its most basic level, an inspection is defined as, a visual examination and some manual checks. You're just determining the current condition of an aircraft or a component.
Pretty straightforward on the surface.
But the philosophy, it runs much deeper than that definition. It's really an exercise in, let's call it, preemptive failure reduction.
Ooh, I like that phrasing, preemptive failure reduction. Because this inspection mandate, it isn't just a box to tick for compliance, is
Not
it?
at all. It's a commitment. A
Yeah.
commitment to maintaining that aircraft in the best possible condition it can be in.
And our sources, they really hammer this home.
Yeah.
A maintenance program needs inspections that are both thorough and frequent, repeated.
Definitely. If you, as the AMT, start treating inspections as just irregular or, haphazard checks, maybe only done when something obviously breaks,
You're asking for trouble.
you are guaranteeing the gradual deterioration of the entire aircraft and, well, the cost calculation there. It's brutal. The time you spend fixing a major failure or repairing an aircraft that's been abused by rushed or skipped maintenance,
Yeah.
it just always outweighs any time you thought you saved by cutting corners on routine checks. Always.
So the goal is proactive, always thinking ahead, detecting and correcting those minor defects, maybe some excessive wear early on in its life cycle. That's what really cuts down on operating failures later.
Exactly. It's a fundamental shift in perspective. You're moving from just fixing what's broken to actively preventing the breakage in the first place.
Makes sense.
And that whole proactive philosophy, it dictates how we structure the inspection periods themselves, those intervals. They're not universal at all.
I imagine they vary quite a bit.
Hugely. Depends on the specific aircraft model, its operating environment. Is it flying in corrosive salt air or dry desert? And the type of flying it's doing. Commercial use. Private.
So as the AMT, where do you even start?
First step, always. Consult the manufacturer's specific instructions for that aircraft. That's your baseline.
Got it. And when we look at how maintenance management actually schedules this work, the intervals usually fall into one of two main time-based systems, right?
That's right. The first one you'll often see is the calendar inspection system.
Okay, calendar-based, how does that work?
Pretty much like it sounds. An inspection gets triggered when a specified number of calendar weeks or months runs out. Tick-tock. And maintenance management often likes this system because it gives them a really efficient, predictable schedule. Doesn't matter how much the aircraft actually flew in that time.
Ah, I see. So it helps with planning crews, ordering parts.
Exactly. It keeps things consistent year-round from a management standpoint.
Okay. But then on the flip side, especially for planes that fly a lot, like flight school trainers, charter planes, maybe air cargo.
Right, high-utilization aircraft. For those, you often see the flight hours inspection system.
So this one's based purely on time in the air.
Correct. The inspection is mandated only after a specified number of flight hours have piled up on the airframe or engine hobs meter.
Okay, but what about parts within the plane that have their own specific lifespan measured in hours, like a particular gearbox or something?
Good question. That's key. You don't pull the aircraft out of service just for that one part hitting its limit.
So how do you handle it?
You synchronize it. The component's scheduled replacement gets timed to happen during the main inspection interval, whether that's calendar or flight hour based, that falls closest to that component hitting its hourly limit.
Ah, smart. You bundle the work together.
Right. It ensures comprehensive work gets done all at once, minimizes unnecessary downtime for the aircraft, and keeps everything operating safely.
So whether it's calendar or hour-based, the system has to be systematic, thorough. But it's not just about turning wrenches and checking things off, is it?
Yeah.
There's a massive pillar of accountability here, record keeping.
Oh, absolutely. Which brings us straight into documentation, #tag2, documentation and logbook management. Before any tool even gets near the aircraft, your work as an AMT starts with paper or, digital files these days. Preparation is it's absolutely crucial.
What does that prep involve?
You have to access and really study a fair bit of paperwork and reference info. That means reviewing previous logs, what was done last time, understanding the specific checklist required for this inspection, and confirming you're up to date with any new manufacturer publications or FAA requirements.
And let's stress a really critical practical step right here, something easy to miss.
Okay.
Before you start cleaning the aircraft, before you even think about opening an access panel, you must note any visual evidence of fluid leakage, oil, fuel, hydraulic fluid,
Yeah.
anything.
Yes. Because if you wipe that area clean first.
You might destroy the only easily readable clue that there's a serious problem, like a weeping fitting or a tiny crack in a line.
Exactly. Note it down, maybe take a photo, then you clean it. Document first.
Okay, so the history, the health, the legality of the aircraft, it all lives within its aircraft logs, right?
That's the heart of it. And that term logs, it's pretty broad. It can mean those small, traditional physical logbooks you see in, say, a Cessna 172.
Yeah, the little 5x8 ones.
All the way up to these huge, multi-volume, 3-ring binders or sophisticated digital record systems kept for big transport jets.
And what exactly do they record?
All the significant events, total time on the airframe, time on each engine, time on major components and accessories. It's the aircraft's entire life story, technically speaking.
And crucially, this is where you prove compliance with the law.
Absolutely. The logs are the only official evidence showing compliance with those mandatory FAA airworthiness directives, the ADs. And often, just as important, the manufacturer's service bulletins, or SBs.
Right, the AD is the absolute legal requirement. The SB is often the manufacturer's recommended fix, which sometimes becomes mandatory later via an AD.
Correct. And here's something every AMT student needs to grasp, not just technically, but financially.
Sure.
A logbook entry isn't just a note saying, I checked this. It's a legal, transferable instrument of commerce. The organization, the completeness, the professional appearance of those logbooks, it directly impacts the aircraft's market value.
Wow, okay, so messy logs can cost real money.
Big time. Messy, incomplete, illegible logbooks, they're a huge red flag. They signal potential neglect, maybe a lack of care by the owner or previous mechanics. It can easily knock tens of thousands, even hundreds of thousands, off the resale price of an aircraft.
That's a serious responsibility.
Yep.
So once your inspection is done, the logbook entry you make is your official certification.
It is the legal certification of airworthiness. It formally returns that aircraft to service. And there's a clear mandate on that entry.
Let me guess.
Clarity. Absolute clarity. It has to be easily understood by anyone reading it years from now. If you're handwriting it, and many still are, your penmanship needs to be excellent, legible, your description's precise and unambiguous.
Because you're creating a historical legal record.
Exactly. Future mechanics, future owners, maybe even accident investigators. Their work, maybe even their lives, could depend on understanding your notes perfectly.
Okay, so the foundation of the actual inspection process itself, it relies on a checklist, right? You can't just wing it.
Never. You must use a checklist, always. Whether it's the one provided by the manufacturer, maybe a custom checklist that's been approved by the FAA for a specific operation, or at a minimum, you need to cover the scope defined in Appendix D to 14 CFR Part 43. That's the baseline standard.
Let's walk through a few examples from those checklist groups in Appendix D, just to get a feel for the depth we're talking about.
Yeah.
Like the fuselage hull group.
Okay, so you're not just glancing for obvious dents. You're checking the fabric or the skin for any signs of deterioration, maybe corrosion starting under the paint, distortion from stress. You're checking the security of all the attachments, the fittings. Is that antenna base secure and sealed? Is there any oil soaking into the fabric which could weaken it?
Right, detailed stuff. What about the cabin cockpit group?
There, the focus is heavily on safety items and the instruments. Are the seats and safety belts securely attached? Are they in good condition? No fraying? Buckles work? And the instruments, are they properly marked? Do the colored arcs, the green, yellow, red lines, correctly show the normal and caution and danger operating ranges?
And do they actually work correctly?
Crucial. Does the needle move smoothly? Does it indicate accurately? You need to verify operation.
Okay, now the engine nacelle group. This feels critical.
Extremely. Obviously, you're looking for any visual evidence of leaks, oil, fuel, coolant, but you have to go deeper than the surface. You're performing internal checks,
Like what?
like running a cylinder compression test. That tells you a lot about the health of the valves and the piston rings. You're inspecting magnetic drain plugs and oil filter screens for any metal particles.
Finding metal bits is bad news, right?
Very bad news. Shiny flakes, magnetic fuzz. That's an immediate grounding event. It signals something is coming apart inside the engine. You have to investigate further before it flies again.
What else in the engine group?
Don't forget the whole support structure. You inspect the engine mount itself for any cracks or looseness. Those can indicate high stress or vibration problems. And you check all the controls. Throttle, mixture, prop controls. Do they have correct, full, smooth travel? And are they properly safety?
Safety meaning?
Meaning secured with lock wire or cotter pins, so critical bolts or connections can't vibrate loose or move inadvertently. It's a fundamental safety practice.
Got it. And finally, the parts that hit the ground. The landing gear group.
Yep, making sure all the gear units are secure. Checking the oleo strut, that's the air oil shock absorber, for the correct fluid level and proper inflation. Looking closely at the wheels for cracks. Checking the wheel bearing condition. Are they smooth or gritty?
And the tires, obviously.
Meticulously. Inspecting tires for cuts, bald spots, uneven wear. Checking the pressure. And don't forget, the brakes, are they adjusted correctly? Is there enough pad left?
Okay, and the wing center section.
That demands looking inside where possible. Checking the internal structure, the spars, the ribs, for any signs of cracking, bending, or corrosion. And confirming the control cables that run through there are tensioned correctly, that they're not frayed, and that they're routed cleanly through all their guides, fair leads, and pulleys without rubbing.
Wow. Okay, so using that checklist systematically, it's like the AMT's insurance policy against missing something critical.
It absolutely is. It ensures thoroughness and consistency every single time. #Tag3. The regulatory framework and technical data. Now, to actually perform everything on that checklist correctly and to make those proper logbook entries, you, the AMT, have to navigate this huge library of aeronautical publications.
Right. It's not just intuition. There are official sources.
Definitive sources. These are the authorities that guide every single action you take. We're talking manuals, parts catalogs, the Code of Federal Regulations, CFRs, airworthiness directives, ADs, advisory circulars, ACs, various specifications. It's a lot.
Let's try to break down the hierarchy here, maybe starting with the manufacturer's own documents. What are service bulletins, SBs?
Okay, SBs. These are detailed instructions put out by the manufacturer for service adjustments, maybe modifications or specific inspections they recommend. They often give you critical details like the estimated man-hours it should take and where to get the parts needed.
Are they legally mandatory, like ADs?
Not initially, no. They start as recommendations. However, if a safety issue persists, or the manufacturer identifies a significant problem, ignoring SBs, especially repetitive ones, can often lead to the FAA issuing a mandatory AD based on that SB later on. So you treat them very seriously.
Got it. Then come the core manuals, right, like the maintenance manual.
Exactly. The maintenance manual gives you the complete, detailed instructions for maintaining the systems and components while they're installed on the aircraft.
So things like
lubrication procedures, what type of grease goes where, how often, required pressures for hydraulics or tires, component tolerances, what's the acceptable wear limit, procedures for leveling the aircraft for rigging checks or balancing flight controls, special repair methods approved by the manufacturer, and of course the inspection frequencies and details tied to the overall program.
Okay, so that's for stuff on the plane. What if you take a major component off the plane for work?
Good distinction. If you remove a major unit, say a landing gear actuator, an engine fuel control, a generator, you'll usually turn to the overhaul manual for that specific component.
And that gives you
detailed step-by-step instructions. How to completely break it down, inspect every internal part, perform necessary repairs or replacements, and then correctly reassemble and test it.
Does it cover everything you might remove?
Not quite. There's a key exclusion. Simple sort of... That's the job of the Illustrated Parts Catalog, IPC. Essential reference. It gives you component breakdowns, exploded views showing how things fit together, cutaway illustrations sometimes, makes identifying and ordering the correct part much easier.
And finally, all the wiring.
All detailed in the wiring diagram manual. Every wire, connector, pin number, it's all in there. But
Yeah.
here's where standardization becomes your absolute best friend as an AMT.
How so?
Almost all modern aircraft technical data, especially for transport category and many newer GA aircraft, is organized according to a system called ATA iSpec 2200. It used to be called ATA 100.
ATA, Air Transport Association.
Right. They developed this standard, and it's a total game changer for technicians. It standardized the format and the chapter numbering for technical data, regardless of who built the aircraft. Boeing, Airbus, Embraer, Textron, Gulfstream. They all use the same basic system.
So Chapter 24 in a Boeing manual covers the same system as Chapter 24 in an Airbus manual.
Exactly. That standardization is incredibly powerful. As you study, start learning these key chapter numbers. Like you said, Chapter 24 is always electrical power. Chapter 32 is always landing gear.
What are some other common ones?
Well, Chapter 5 covers time limits and maintenance checks. Chapter 21 is air conditioning. Chapter 27 is flight controls. Chapter 34 is navigation. Chapter 71 covers the power plant, the engine itself, and its installation. Chapter 72 is the engine. You get the idea.
Yeah, I can see how that saves a massive amount of time.
Huge. If you know the ATA system, you can move between different aircraft types and find the critical information you need almost instantly. It drastically reduces errors and time spent just searching for data.
Okay, so that's the manufacturer and industry side. Now let's shift to the ultimate authority, the FAA and the regulations.
Right. The Code of Federal Regulations, specifically Title 14, Aeronautics and Space, often just called the CFRs. These rules were established by Congress, implemented by the FAA, and their whole purpose is to provide for safe and orderly flight operations.
And for mechanics.
Every single maintenance action you perform must comply with the relevant provisions of these CFRs. No exceptions.
And the FAA's most direct tool for ensuring safety on specific aircraft models is the Airworthiness Directive, the AD, right?
Correct. An AD is issued by the FAA when they determine that an unsafe condition exists or is likely to develop in a specific aircraft design, engine, propeller, or appliance. Compliance is absolutely mandatory under 14 CFR Part 39.
Unless
Unless a specific exemption is formally granted by the FAA, which is rare for safety of flight items. If you ignore an AD or don't comply by the deadline, that aircraft is instantly legally unairworthy. Period.
How quickly do you have to comply?
ADs generally fall into two categories. There are emergency ADs, which usually require immediate compliance before further flight. These often ground entire fleets until the fix is made.
Okay, urgent.
And then there are less urgent ADs. These still identify an unsafe condition, but the risk isn't deemed immediate, so they allow a longer defined compliance period, maybe a certain number of flight hours, or by a specific calendar date.
And is compliance usually a one-and-done thing?
It can be. Some ADs require a one-time fix, maybe installing a modified part or performing a specific inspection just once. But many ADs require recurring action. This could be a special inspection that has to be repeated every 50 flight hours, or an ultrasonic check required every 12 calendar months, for example. You have to track those recurring ADs meticulously.
This whole regulatory framework raises a fundamental question. What exactly defines the official, approved configuration of any specific airplane model? Where is that written down?
That's the Type Certificate Data Sheet, or TCDS. This is a foundational document. When an aircraft manufacturer gets a new model certified by the FAA, the TCDS is issued. It describes the aircraft's type design, its core specifications, and sets forth all the limitations required by the CFR part it was certified under.
So when you're doing an inspection, a big part of it is checking against this TCDS.
A crucial part. It's called the conformity check. You, the inspector, must ensure that the aircraft, including its major components like engines and propellers, conforms exactly to the specifications listed in its specific TCDS.
Let's look at the kind of detail we're talking about. You mentioned an example, TCDS.
Right. A TCDS is like a technical Bible for that specific model. It will specify the exact engine model allowed, say a Lycoming O320E1C, and its operating limits may be 150 horsepower at 2,700 RPM max.
Fuel type.
Absolutely critical. It mandates the minimum fuel grade. If the TCDS says 8887 minimum octane is required, and you find someone has been fueling it with, say, automotive gasoline without proper approval, that aircraft does not conform. It's unairworthy.
What about operating limits?
All the key speeds are listed. V never exceeds speed, maybe 173 knots. VNOMAX structural cruising speed, V maneuvering speed. If the markings painted on the airspeed indicator in the cockpit don't match the TCDS values, that's a nonconformity.
And you mentioned something about control surfaces. This seems incredibly precise.
It is. This is one of the most critical details for an AMT doing rigging or inspection. The TCDS specifies the exact required control surface movements. For the ailerons, for example, it might say, up travel 29 degrees plus or minus 1 degree, down travel 14 degrees plus or minus 1 degree.
That tolerance, plus or minus 1 degree, is razor thin.
It really is. So if you measure those ailerons after maintenance and you find one moves 30.5 degrees up, technically, you have exceeded the type design limit defined in the TCDS.
And the consequence?
You have just grounded that airplane. It does not conform to its type certificate. That's how strict the accountability is to that document.
Wow. Okay, one last piece here. What if someone makes a major change to an aircraft after it leaves the factory? Something not covered in the original TCDS.
That requires a supplemental type certificate, or STC. If an owner wants to install, say, a different engine model, or add wingtip fuel tanks, or install fancy new avionics not offered originally, they need to get an STC approved by the FAA for that specific alteration on that specific aircraft model.
And once it's approved and installed,
that STC paperwork becomes a permanent part of the aircraft's records, right alongside the TCDS. It officially amends the original type design for that particular aircraft or fleet. #Tag 4, required inspection programs.
okay, let's talk about the different types of inspections that are required. The process actually starts before the mechanic even gets involved, right? With the pilot?
That's right. The ultimate legal responsibility for determining airworthiness before each flight rests with the pilot in command, the PIC.
Yeah, how do they do that?
Primarily through the pre-flight inspection checklist found in the pilot's operating handbook, the POH. This includes the physical walk-around check, looking for obvious issues like flat tires, fuel leaks, damage, and also a quick review of the maintenance records, the logbooks, to make sure no required inspections or ADs are currently due.
Is there a post-flight check too?
A post-flight inspection is always highly recommended, especially to catch issues that might have developed during the flight, but it's usually voluntary, not legally mandated like the pre-flight.
Okay. But for the AMT, the real scheduled work centers on the annual and 100-hour inspections, correct? Governed by 14 CFR Part 91.
Exactly. Those are the big ones for most general aviation aircraft. The annual inspection is required for almost all aircraft once every 12 calendar months, regardless of how it's used.
And the 100-hour.
The 100-hour inspection is only required if the aircraft is used for commercial purposes. The two main triggers are carrying passengers or property for hire or providing flight instruction for hire.
So a private owner just flying themselves around only needs the annual.
Correct, unless they rent it out or use it for lessons.
Now, interestingly, you mentioned the scope of the 100-hour is basically the same as the annual. They both follow that detailed checklist in Appendix D of Part 43.
Functionally identical in terms of what needs to be checked, but there are two huge differences between them.
What's the first one?
Personnel. Who is allowed to perform the inspection and sign it off? A licensed airframe and power plant mechanic, an A&P, can perform and sign off a 100-hour inspection.
Okay, but the annual...
The annual inspection is a step up. It must be conducted and signed off by an A&P mechanic who also holds an inspection authorization, commonly called an IA.
And getting an IA is a bigger deal.
Yes. It requires more experience, passing a rigorous FAA knowledge test, and it signifies a higher level of responsibility and authority. The FAA entrusts IAs with the final word on annual airworthiness for most GA aircraft.
Okay, so difference one is who can do it. A&P for 100-hour, A&P with IA for annual. What's the second big difference?
It involves overflying the time limit. There's a small but very important exception for the 100-hour inspection.
Which is?
14 CFR Part 91 allows an aircraft due for its 100-hour inspection to be flown up to 10 hours beyond that 100-hour limit.
Why?
Specifically and only to fly the aircraft to a location where the inspection can actually be performed. Maybe the maintenance base is a few hours away?
A ferry allowance. Does that apply to the annual too?
Absolutely not. That 10-hour grace period does not apply to the annual inspection. If the 12 calendar months are up for the annual, that plane is grounded, period. No ferry flights allowed without a special permit.
That's a critical distinction. Okay, the annual is pretty comprehensive, and it can ground a plane for a while. Are there alternatives for operators who need to keep their planes flying more consistently?
Yes, especially for busy flight schools or charter fleets where downtime equals lost revenue. They can apply for FAA approval to use a progressive inspection program.
Progressive. Meaning it's done in stages.
Exactly. This program takes the exhaustive scope of a full annual inspection and breaks it down into smaller, more manageable phases or segments, typically 4 to 6 phases.
And the benefit.
You can complete these smaller phases sequentially, often overnight or during brief maintenance periods, without taking the aircraft out of service for a long stretch like a traditional annual. It maximizes the aircraft's availability.
But you can't just decide to do this yourself, right?
Definitely not. To use a progressive program under CFR 91.409D, the owner or operator has to submit a formal written request and get specific approval from their local FAA Flight Standards District Office, the FSDO.
What does the FAA need to see?
They require a detailed manual outlining the entire program, the schedule for each phase, the specific procedures to be followed, who's responsible, and the quality control measures. And critically,
Yes.
all the phases combined must cover everything required in an annual, and the entire cycle of all phases must be completed within 12 calendar months. If you don't finish the cycle in time, the annual is considered expired and the plane is grounded.
Okay, so that's progressive. What about the really big planes, airliners, large corporate jets?
For those, especially large or turbine-powered aircraft, often operating under Part 135 or 121, we move into continuous inspection programs. These are even more complex and sophisticated systems.
And these are the ones with the letter checks, right? A, B, C, D checks.
That's the common airline terminology, yes. They're built around increasing levels of inspection depth and frequency.
Can you give us a quick idea?
Sure. An A-check is the least comprehensive, maybe done every few hundred flight hours. It's often an overnight check involving basic servicing, fluid checks, maybe some system checks, light lubrication. Okay, what about a C-check? A C-check is much more involved. It requires significant downtime, maybe a week or two. It involves opening up many more access panels, removing seats and cabin interiors for structural inspection, performing detailed functional checks, and looking much deeper into systems, usually done every 18-24 months or so.
And then the D check. I heard this is massive.
It is the pinnacle. The D check, sometimes called a major overhaul visit or heavy maintenance visit, HMV.
Wait, you said it involves nearly disassembling the entire aircraft, removing engines, landing gear, flight controls, stripping paint, inspecting almost every structural rivet. That sounds less like a check and more like a factory rebuild.
It's pretty close. The D check is the ultimate deep dive into the aircraft's health. It's incredibly comprehensive. Major disassembly, removal and overhaul of numerous components, extensive NDI scrutiny of the structure, everything gets looked at.
How often does that happen?
Because of the immense cost and labor involved, we're talking potentially months of work and thousands upon thousands of man-hours. Our sources indicate that a D-check might only occur maybe 3 to 6 times during the entire service life of a large transport aircraft, maybe every 6-10 years, depending on the program.
Wow. Okay. Are there any other time-based checks we need to know about?
Yes, a couple of important ones for instrument flight. Aircraft operating under instrument flight rules, IFR, in controlled airspace, have additional requirements.
Such as?
Their altimeter and static pressure systems, which provide altitude information, and their ATC transponder, which reports position and altitude to air traffic control, must be tested and certified for accuracy every 24 calendar months.
And who does that?
This requires specialized test equipment and must be done by appropriately certified individuals or repair stations. It's crucial for maintaining safe separation in busy airspace. #TAG5. Conditional inspections, special events. All right, so the scheduled inspections, annual, 100-hour, progressive, continuous, they account for normal wear and tear over time.
Right, the expected stuff.
But then there are conditional inspections. These aren't on a set schedule. They're triggered by specific, usually external, non-routine events that might have damaged the aircraft or affected its airworthiness.
And when one of these events happens?
Your first step, always, is to immediately consult the aircraft's specific maintenance manual. It will outline the detailed procedures required for that particular type of event. Don't guess.
What's a common example of an event needing a conditional check?
Probably the most common is the hard or overweight landing. There's a subtle difference. A hard landing is a really rough impact, but it happens at or below the aircraft's maximum design landing weight. An overweight landing is any landing, even a smooth one, that occurs above the certified maximum landing weight.
Both put a lot of stress on the airframe, though.
Exactly. Severe stress, particularly on the landing gear and wing structure. So you're looking for subtle visual signs of damage. The easiest thing to spot usually is wrinkled wing skin, often near the wing root where it joins the fuselage, or along the main spar lines. Look very carefully for fuel leakage along riveted seams. If the sealant between the panels broke under the flex, fuel will seep out. Check internal structures like spar webs, bulkheads near the gear attachments, and the skin around the engine nacelles for any buckling or cracking.
And finding any of that means.
It mandates a much more extensive inspection. You might need to do complex alignment checks of the landing gear, maybe even wing symmetry checks, using specialized tooling and procedures from the SRM.
Okay, what about forces in the other direction, like hitting really bad turbulence?
Right, severe turbulence or over-G events. Here, the excessive air loads put abnormal stress, often bending stress, on the wings and the tail surfaces.
So similar signs, wrinkles.
Yes, but specifically you're looking for excessive buckles or wrinkles that show a permanent set, meaning the metal is bent and doesn't spring back to its original shape. Look carefully on both the upper and lower wing surfaces.
How do you assess if the structure itself was overloaded?
Sometimes visual inspection isn't enough. The manual might require you to perform some localized disassembly. You might have to remove a few rivets in the suspected overstress area and carefully examine their shanks under magnification. Are they sheared? Are they elongated? That tells you the joint thaw forces beyond its design limit.
Fuel leaks again.
Fuel leaks are always a big indicator after turbulence too, suggesting the sealant broke down from flexing. And pay extremely careful attention to the empennage, the tail section, especially where the horizontal and vertical stabilizers attach to the fuselage. Those joints experience extreme bending moments during turbulence or high G maneuvers.
Okay, let's switch from physical impact to environmental trauma. What about a lightning strike?
Relatively rare, but serious when it happens. The inspection needs to focus on the path the electrical current took through the airframe.
Aluminum conducts well, right?
It does, usually without major damage to the metal itself. But the concern is where the current passes through non-metallic structures like fiberglass radomes, composite fairings, or flight control surfaces. Look for signs of burning, pitting, or erosion where the current entered or exited.
What else needs checking after a strike?
You absolutely must check the integrity of all the bonding straps. These are the metal braids or straps that electrically connect different parts of the aircraft to dissipate static electricity and provide a path for lightning. Make sure they aren't burned or broken. Also, check the static discharge. Wicks those little points, usually on the trailing edges. Make sure they're intact.
Okay. Another environmental hazard. Fire damage.
Fire damage is particularly insidious, very sneaky, because even if the visible damage seems minor, maybe just scorched paint, the heat itself can permanently ruin the strength of metals.
How so?
Many aircraft structural components, especially high-strength aluminum alloys and certain steel parts, are heat-treated at the factory to achieve their required strength and hardness. Exposing them to excessive heat, even without direct flame contact, can reverse that heat treatment, essentially annealing the metal and making it much weaker even if it looks fine.
So how on earth do you tell if the metal's strength is compromised if you can't see physical damage?
This is where NDI becomes essential. For aluminum structure that you suspect got too hot, the go-to tool is often a conductivity tester, which usually uses eddy current principles.
Conductivity, how does that relate to strength?
There's a direct correlation. As heat degrades the temper or hardness of the aluminum alloy, its electrical conductivity changes predictably. So you take readings on the suspect area and compare them to readings from a known unaffected area of the same alloy. A significant drop in conductivity tells you the heat definitely affected the material's temper, meaning its design strength is likely compromised.
What about steel parts?
For heat-treated steel structures, you typically use a Rockwell C hardness tester. Again, there's a direct relationship between the surface hardness of the steel and its tensile strength. If the hardness reading is below the specified minimum after suspected heat exposure, the part is compromised.
Let's integrate a type of operation you mentioned that AMT students might overlook. Aerial application aircraft. Ag planes.
Yes, good point. These aircraft live in a uniquely hostile environment. They face two big challenges: accelerated fatigue and accelerated corrosion.
Why?
First, the chemicals they spray are often highly corrosive. Residue gets everywhere. Second, their operational cycle is brutal. They might do 50 or more takeoffs and landings per day, often from rough, unimproved grass or dirt strips. That's an incredibly high number of stress cycles on the landing gear and the airframe structure.
So they need more frequent checks.
Much more frequent, especially focused inspections of the landing gear, the lower fuselage structure, wing attachment points, and regular, often accelerated changes of engine air filters because they ingest so much dust and debris. Corrosion control is also paramount.
Okay. What about flood damage? Water getting into the plane.
The severity depends on a few factors. How high did the water level get? Was it freshwater or saltwater? Saltwater is a nightmare because it's such a powerful electrolyte driving rapid corrosion. And crucially, how long was the aircraft exposed before it could be dried out?
What's the usual procedure?
For any parts that were actually submerged, it generally requires complete disassembly of those components, rigorous cleaning, thorough drying, often using special ovens or desiccants, and then application of corrosion-inhibiting compounds before reassembly.
What about non-metallic parts? Carpet, seats, insulation?
Many non-metallic parts, especially avionics, instruments, upholstery, and insulation, often require outright replacement after significant water immersion. Water gets trapped, promotes mold, and can cause irreparable damage, especially to electronics. It's a huge, expensive job to recover a flooded aircraft properly.
One last regulatory thing here. What if an aircraft is found unairworthy, maybe due to damage, or an overdue inspection, but it's still safe enough to fly once to get it fixed?
Ah, yes. In that specific situation, where the aircraft doesn't meet its type design or is non-compliant, but you, as the mechanic, determine it's still in a condition for safe operation for a specific flight.
You can't just let them fly it, right?
No. You need to apply to the local FAA FSDO for a special flight permit, which is often called a ferry permit. This is issued under the rules in 14 CFR Part 21.
And what does it allow?
It typically authorizes a one-time flight under specific conditions or restrictions for purposes like flying the aircraft to a base where repairs or maintenance can be performed for delivering a new aircraft, for evacuation from impending danger, or sometimes for customer demonstration flights. Hashtag Tech 6, non-destructive inspection NDI-NDT techniques.
Okay, we've mentioned conditional checks needing NDI. Let's actually explore these techniques now. Non-destructive inspection, you hear NDI, sometimes NDT for non-destructive testing. What's the core goal here?
It's a singular, really powerful goal to determine the airworthiness, the condition, the integrity of a component or structure without damaging it, without rendering it unairworthy just by checking it.
Makes sense. You don't want to break it to see if it's broken.
Exactly. NDI is this fascinating fusion of applied science and, honestly, a bit of art based on experience. And its success relies almost entirely on the skill of the personnel involved.
So not just anyone can grab an NDI machine and start testing.
Absolutely not. Especially for the techniques that require significant interpretation of the results, things like eddy current, ultrasonic testing, radiography, X-ray. The people performing these tests and interpreting the signals must be properly qualified and certified.
Certified to what standard?
There are established industry standards, like NAS 410, formerly MIL STD 410, used often in defense and aerospace, or ATA Specification 105, used in the airline world. These standards define different levels of qualification based on training, experience, and examination. This isn't beginner work. It demands real knowledge, proven skill, and deep experience to do reliably.
Okay, where does NDI really start? What's the most fundamental method?
It starts with visual inspection. That's the first line of defense, the most common NDI method used every single day.
Just looking closely.
Looking very closely, often enhanced with simple aids. A good, bright, focused light source is essential. A mirror for looking into hidden areas. And a magnifying glass, a 10-power magnifier, is highly recommended in most maintenance manuals for detailed visual checks.
Is there a specific technique even for just looking?
Yes, absolutely, especially when you're searching for very fine surface cracks, like fatigue cracks starting near rivet holes. The technique matters. You should direct your light beam at a shallow angle to the surface you're inspecting.
Why shallow, like 5 to 45 degrees, the sources say?
Exactly. That low-angle light doesn't reflect directly back at you. Instead, it casts tiny shadows within the crack itself, making that discontinuity, that fine line, really pop out and become visible. If you shine the light straight down, 90 degrees, it can actually wash out the detail and make the crack harder to see.
Good tip. But visual inspection has its limits, right?
Absolutely. The biggest limitation. A lack of visible surface defects does not mean there isn't damage lurking underneath. Subsurface cracks, internal corrosion, delaminations in composites. Visual won't find those.
So for looking inside things without taking them apart.
That takes us to the next step up in visual aids. The borescope inspection.
Ah, the little cameras on flexible tubes.
Right. Borescopes, or the more advanced videoscopes, are essential tools for internal visual checks without major disassembly. You thread these rigid or flexible fiber optic tools, or video probes, through small access ports like spark plug holes in piston engines, or special borescope ports built into turbine engines.
What are they typically used for?
All sorts of internal inspections. Peering inside jet engine combustion cans to look for cracks or burn through, inspecting turbine blades for nicks, cracks, or foreign object damage, FOD, checking the internal condition of hydraulic cylinders or actuators for pitting, scoring, or seal damage. Even sometimes used to retrieve dropped hardware foreign object retrieval. Very versatile tools, #Tech7. Detailed NDI methods and application.
Okay, let's move beyond visual into the more specialized NDI methods that use chemistry or energy. First up, liquid penetrant inspection. What's this good for?
Liquid penetrant, often called dye penetrant or just PT, is used to detect defects that are open to the surface defects only. And it works on non-porous materials that includes most metals, many plastics, ceramics, things used widely in aircraft construction.
Surface-only, non-porous materials. Got it. How does it actually work? What's the process?
The process is very methodical, and honestly, the single biggest failure point for new technicians is improper surface preparation. It has to be right.
Step 1.
Step 1, thorough cleaning. You absolutely must remove all contaminants, grease, oil, paint, dirt, scale from the area you want to inspect. The penetrant needs a clean path into any cracks.
Okay, clean surface. Then what?
Then you apply the penetrant itself. This is a brightly colored or fluorescent liquid with very low surface tension, so it wants to seep into any tiny openings. You let it sit for a specific dwell time, usually 10-30 minutes, to allow it to penetrate fully.
After it dwells.
Next, you meticulously remove the excess surface penetrant. This is critical. You want penetrant in the cracks, but not smeared all over the surface. You use specific cleaners or emulsifiers and wiping techniques.
And dry it.
Dry the part thoroughly, and finally, you apply the developer.
What does the developer do?
The developer is usually a fine white powder suspended in a solvent or used dry. It acts like a blotter paper. It draws the penetrant liquid trapped in the cracks back out to the surface through capillary action, creating a visible indication against the white background.
And how do you interpret what you see?
The interpretation is based on the indication's size, shape, and brightness. Generally, the defect size relates to how brilliant the indication is. Deeper, wider cracks hold more penetrant, so they produce broader, brighter, more intense indications. Fine, tight cracks might show up as faint lines.
You mentioned colored or fluorescent penetrant.
Right. You have two main types. Visible dye penetrant is usually bright red, so you see red indications on the white developer under normal white light. Fluorescent penetrant contains dyes that glow brilliantly, usually a bright yellow-green when viewed under an ultraviolet or black light.
Is one better?
Fluorescent penetrant generally offers significantly greater sensitivity. It can reveal much finer cracks that might be missed with visible dye. That's why it's very common in aerospace for critical components.
Can you get fooled by things that look like cracks, but aren't?
Absolutely. You have to learn to distinguish true defect indications from false indications. A really common false indication happens if you do a poor job washing off the excess penetrant. You'll see broad, smeared patterns of color that aren't sharp lines.
What else?
Another common one is penetrant accumulating at mechanical joints, like where a bearing race is press fit into a housing. You'll see a regular line or shape right at the joint line. These are usually identifiable by their regular shape and location and shouldn't be mistaken for cracks in the base material. Experience helps differentiate.
Okay, that's liquid penetrant for surface cracks in non-porous stuff. What about finding cracks in steel parts?
For that, the go-to method is magnetic particle inspection, or MPI. Key thing. This method works exclusively for ferromagnetic materials, basically materials that can be strongly magnetized. That means iron, steel, and some of their alloys. It won't work on aluminum, magnesium, titanium, copper, etc.
Ferromagnetic only. How does it work? What's the principle?
You intentionally magnetize the part. This creates magnetic lines of flux flowing through the material. If there's a discontinuity, like a crack, a seam, an inclusion near the surface, it disrupts the flow of these magnetic lines.
Like a rock in a stream.
Exactly like that. The magnetic flux has to detour around the discontinuity, and some of it leaks out of the surface right at the defect location. This is called flux leakage.
And how do you see that leakage?
You apply finely ground ferromagnetic particles, basically tiny iron filings, either as a dry powder or suspended in a liquid carrier onto the surface while it's magnetized. These particles are attracted to the areas of flux leakage, and they build up directly over the discontinuity, forming a visible outline or indication of the defect.
Now, you mentioned something critical earlier about flux direction.
Yes, this is the most critical principle for you to grasp about MPI. To reliably detect a defect, the magnetic lines of flux must pass approximately perpendicular to the major dimension of the defect.
Perpendicular. So if the crack runs north-south, the magnetic field needs to run east-west across it.
Precisely. Think of that crack as a dam again. If the magnetic current, the river, runs parallel to the dam, it just flows right past without much disturbance. You get little or no flux leakage, no particle buildup, no indication.
But if the current hits the dam head-on,
If the magnetic field lines cross the crack perpendicularly, they're forced to leak out around it. That's when you get strong flux leakage and a clear particle indication.
so since cracks can run in any direction, how do you ensure you find them all?
You almost always need to perform two separate magnetization steps, with the magnetic field oriented roughly 90 degrees apart in each step.
What are those two steps typically called?
First is usually circular magnetization. This is done by passing high amperage electrical current directly through the part itself or through a central conductor placed inside a hollow part. This creates a circular magnetic field within the part. This field is best for detecting defects that run longitudinally or parallel to the direction of the current flow.
Okay, circular for longitudinal defects. That's a second step.
Longitudinal magnetization. Here, the part is placed inside a coil or solenoid carrying electrical current. This creates a magnetic field that runs longitudinally from one end of the part to the other, parallel to the axis of the coil. This field is best for detecting defects that run transversely or perpendicular to the long axis of the part.
So you do both to cover all
Yeah,
possibilities.
you generally have to, yes. Circular mag, apply particles, inspect. Then longitudinal mag, apply particles, inspect again.
Are there different ways to apply the particles and magnetism?
Yes, the two main methods are continuous and residual. In the continuous method, you apply the magnetic particles while the magnetizing force, the electric current, is still being applied. This generates the maximum amount of flux leakage and offers the highest sensitivity for finding fine defects. It's the most widely used method in aviation.
And residual.
The residual method relies on the part retaining some magnetism, becoming a temporary permanent magnet after the magnetizing current is turned off. You then apply the particles. This only works well on materials with high magnetic retentivity and is generally less sensitive than the continuous method.
One crucial final step after MPI.
Absolutely critical. After the inspection, all ferromagnetic parts must be thoroughly demagnetized. If you leave residual magnetism in the part, it can attract metallic chips or filings during operation. That could cause catastrophic damage if it gets into bearings, gears, or sensitive instruments. Demagnetization is mandatory.
Okay, MPI for steel. What about inspecting conductive materials that aren't magnetic, like aluminum or titanium? We mentioned eddy current inspection for heat damage.
Right. Eddy current, sometimes called electromagnetic analysis or ET, is incredibly versatile. It's used on electrically conductive materials, which includes most metals used in aircraft. It can detect surface and subsurface cracks just below the surface, corrosion, especially hidden corrosion that causes material thinning, and as we discussed, it can also determine the material's alloy type or its heat treat condition.
How does it work without magnets?
It uses electromagnetism. A probe containing a coil of wire is brought near the surface of the part. An alternating current is passed through this coil, which generates an alternating magnetic field. This primary field, in turn, induces small circular electrical currents within the conductive material of the part itself. These are the eddy currents.
Okay, so you induce these little currents in the part. How does that find flaws?
These eddy currents flow in predictable patterns just below the probe. If they encounter a discontinuity like a crack that interrupts their path, or an area of thinning due to corrosion, or even a change in the material's conductivity due to heat damage, their flow path is disrupted.
And that disruption.
That disruption changes the electrical impedance, resistance, and reactance of the coil back in the probe. The instrument measures this change in impedance and displays it on a meter or a screen, indicating the presence and sometimes the nature of the flaw.
Where is eddy current really crucial in aircraft maintenance.
Oh, many places. It's vital for inspecting multi-layered structures like wing skins for hidden corrosion between layers. It's used extensively for inspecting bolt holes for fatigue cracks radiating from the hole edge. It's critical for inspecting complex, high-stress jet engine components like turbine discs and blades. And as we said, it's the primary method for assessing potential heat damage in aluminum structures by measuring conductivity changes.
Doesn't need calibration.
Absolutely. Like most NDI, accurate eddy current testing requires careful calibration using a reference standard. This standard must be made from the exact same material, alloy, and heat treat condition as the part you're testing, and it must contain known, precisely manufactured flaws like small notches or flat bottom holes of specific sizes to set up the instrument's sensitivity and response correctly before you start inspecting the actual component.
Okay, eddy current for conductive materials. What if we need to look deep inside a part, or maybe check for voids or flaws within the material itself?
For that, we often turn to ultrasonic inspection, or UT. This method uses beams of high-frequency sound energy way above the range of human hearing to probe the material.
Sound waves going through metal.
Yes, high-frequency sound travels quite well through most solid materials. UT can detect internal flaws like cracks, voids, empty spaces, porosity, inclusions, foreign material embedded inside, and delaminations. It can also be used to accurately measure material thickness, which is useful for corrosion monitoring.
How does it find the flaws? What's the main technique?
The most common method used in aircraft maintenance is pulse echo. A small transducer containing a piezoelectric crystal sends a short pulse of ultrasonic sound energy into the part. That same transducer then listens for the echoes reflected back.
Echoes from what?
It listens for echoes reflected from the back surface of the part, but more importantly, it listens for echoes reflected earlier from any internal discontinuities or flaws within the material.
So the timing of the echo tells you where the flaw is.
Exactly. The instrument measures the time it takes for the echoes to return. An echo that comes back very quickly indicates a flaw near the surface. An echo that comes back at the expected time for the material's thickness indicates a reflection from the back wall. By precisely timing the return signals, you can determine the depth of the flaw relative to the front and back surfaces. The amplitude, or strength, of the echo can also give clues about the size and nature of the flaw. It's highly sensitive.
Does the sound travel through air easily between the probe and the part?
No, that's a critical point. High-frequency sound energy does not travel efficiently through air. Air gaps cause almost total reflection. So to get the sound energy from the transducer into the test piece effectively, you need to use a couplant.
Couplant. What's that?
It's usually a viscous liquid or gel. Common ones are oil, grease, glycerin, or even just water applied between the face of the transducer and the surface of the part being tested. The couplant fills the tiny air gaps and ensures good sound transmission. This is absolutely essential, especially for the contact testing method commonly used for field inspections. Without couplant, you won't get a usable signal.
Okay, that covers the main methods for metals. But modern aircraft use a lot of composite structures. How do you inspect those since they're not usually metallic?
Right. Composites present unique challenges because they're often made of layers of fabric, like carbon fiber or fiberglass, embedded in a resin matrix. They don't conduct electricity well, they're not magnetic, and sound behaves differently in them.
So what's the simplest check for composites?
The most basic first-level field evaluation for accessible, relatively thin composite skins, the sources say generally less than about 0.080 inches thick, is tap testing, sometimes called the coin tap test,
You literally tap it with a coin.
or a small, lightweight tap hammer made of plastic or aluminum. You lightly tap the surface across the area of interest and listen carefully to the acoustic response, the ring.
What are you listening for?
If the composite structure is soundly bonded, you'll typically hear a sharp, clear, relatively high-pitched ringing tone. If there's a hidden delamination, a separation between layers, or a disbond, where the skin has separated from the underlying core material, like honeycomb, the sound changes dramatically, becomes a dull, flat, or dead-sounding thud. That change in acoustic response indicates a potential subsurface flaw.
Simple, but effective for some things. What about more advanced methods for composites? Or thicker structures?
For more detailed assessment or looking deeper, we often use methods like thermography,
Thermography.
using heat. Exactly, infrared thermography. The basic idea is you apply a uniform heat source, maybe a heat lamp or a flash lamp briefly, to the surface of the composite part. Then you immediately use a sensitive infrared IR camera to map the surface temperatures as the part cools down.
How does that show flaws?
Defects inside the composite like disbonds, areas of water ingress, trapped water, voids, or crushed core have different thermal properties than the surrounding solid material. They conduct or retain heat differently. These differences show up on the IR camera image as distinct thermal differentials, hot spots or cold spots, revealing the location and sometimes the shape of the hidden damage.
Interesting. Any other key points for composite inspection or repair?
One important thing, especially on high-performance aircraft, relates back to lightning strikes. Many composite structures, particularly on jets, have a fine electrical conductivity mesh, often made of aluminum or copper embedded just below the surface. For lightning strike protection, it helps dissipate the energy safely across the skin. So when you perform a repair on these structures, it's critical that you properly restore the electrical continuity across the repaired area. You'd use an ohmmeter to verify low resistance across the bond lines of the conductive mesh patch.
Good point. Okay, one final inspection area that bridges NDI and basic structure. Weld inspection. How do you check welds?
While sophisticated NDI like radiography or ultrasonics can be used to find internal weld flaws, a lot can be determined just by careful visual inspection of the weld bead itself. The appearance gives valuable clues about the quality.
What makes a weld look good?
A good weld generally has a uniform width along its length. The ripples on the surface should be evenly spaced and consistent, and critically, it needs to show signs of good penetration into the base metals being joined.
How much penetration is required?
It depends on the type of weld joint. For a butt weld, where two edges are joined side by side, the standard requirement is usually 100% penetration. The weld metal must fuse completely through the entire thickness of the base metal. For a filler weld, where you're joining surfaces at an angle, like a T-joint, the requirement is typically 25% to 50% penetration of the base metal thickness.
And what does a bad weld look like visually?
Bad welds often have obvious visual flaws. Maybe it was made too rapidly, the ripples will look long, pointed, stretched out, and there might be signs of porosity, little gas bubbles trapped in the weld. Or if insufficient heat was used, you might see improper penetration, evidence of cold lapse where the weld metal didn't fully fuse with the base metal, and just a generally rough, irregular appearance. Visual inspection is the first essential step for weld quality. #tag outro.
Wow, okay, we have covered a huge amount of ground here. The entire ecosystem of aircraft inspection, really, from that core philosophical mandate for continuous airworthiness, through the massive legal and financial weight tied up in logbook management, the incredible specificity needed to conform to a TCDS.
Down to the degree.
Down to the degree. And then diving into the absolute necessity of these advanced NDI techniques, knowing when and how to use liquid penetrant, magnetic particle, eddy current, ultrasonics.
It's a broad skill set you need. Your work as an AMT fundamentally ensures that continuity of airworthiness. And the difference really between being a student or a novice and becoming a competent, trusted professional, it lies in that ability to move seamlessly between all these areas.
Right. Knowing which AD applies and is current. Knowing exactly which manual to reference, remembering Chapter 32 is landing gear, Chapter 71 is power plant, and then having the hands-on skill to apply the right specialized technique.
Knowing you need to hold that inspection light at a 5-degree angle for cracks, or remembering to apply cup plant before you start that ultrasonic check for an internal flaw, it's connecting the knowledge to the action.
And you now understand that something like a D-check involves taking almost an entire airliner apart, something that happens only a handful of times in its decades-long service life, all to maintain safety. That's the ultimate example of deep, regulated scrutiny.
It truly is.
So let's leave you with this thought, something to take away and apply. Consider this level of professional scrutiny we've discussed. Think about this. What common, everyday item, something totally outside of aviation, requires a similarly complex, multi-year, maybe multi-phase inspection cycle, potentially involving specialized NDI, just to maintain its legal and safe operating status?
Interesting question.
And what would be the functional equivalent of a type certificate data sheet for that item? What document defines its exact, approved, safe configuration? Think about it. And go forth and try to apply this level of diligence, this inspection mindset, to everything you approach.